Okay, calculus class, here we go. This is what I think is one of the coolest topics. There's a lot of cool stuff coming with the next few days, but this is one of the coolest. It's a bit of an algebra fest, but it's necessarily so. So I don't want you to believe in magic tricks as usual. But before I get into it, it starts with a story, as it usually does. And so the story is about a little German kid. I don't want to erase anything here. Named Carl Friedrich Gauss. Carl Friedrich Gauss. And this little guy was a German mathematician, but as a young boy, supposedly, he was kind of a punk in school, right? A real screw off. And he was screwing off as he usually did in class. And his teacher punished him and said, add all the numbers from 1 to 100. Add 1 plus 2 plus ... plus 100. Add all these up, right? Just go stand in the corner and add these numbers up. And a minute later, or not even a few seconds later, little Carl said 5,050. Right now, of course, the teacher didn't believe him, and Carl said, "Yeah, I'm right. Check me." And you may think, well, how did Carl possibly figure out that the number is 1 to 100? So he does 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus... Right, that would take forever. But that's not how Carl did it. What he did is said 1 plus 100 equals 101. 2 plus 99 equals 101. 3 plus 98 equals 101. ... And then finally he got to 50 plus 51 equals 101. Right? There's 50 pairs like this. And he was bright enough to say that 50 times 101 equals 5,050, right? Very clever. Now, is that story true? Nobody really knows. Most people doubt that it's true. But he was one of the key players in the development of this stuff. So today we're going to talk about this. We have to set things up using sigma notation. All right. Now, this is not a new concept for you guys. In fact, it's just another way to write adding. But it's important to write out. So first of all, sigma is the Greek letter that's analogous to, it's Greek for the capital letter S, right? Why do we use that? Because it stands for sum. This is not an E. A lot of people call this an E. It's not an E. That's a sigma. It's important to call it what it is. It stands for sum. For instance, if I wrote sigma, right, and I'm going to say the index I equals 1, and I'm going to go to 7, and I'm just going to add up every one of my i's, right? So the sum from 1 to 7 of I. Well, the first time I do it, I equals 1, so that's 1. The next time, the index goes up by 1, is 2, plus 3, plus 4, plus 5, plus 6, plus 7, right? That's what this sigma notation means. That's it. It's just a faster way to write all the numbers from 1 to 7. Okay. Now I can write it differently. I can write the sum from I equals 1 to 7 of 2i. So whatever my I is, I'm going to double that, and that's what I add up. So this is going to go 2 plus 4 plus 6 plus 8 plus 10 plus 12 plus 14. Right? So I take all my 2i's, and I will go 1, 2, 3, 4, 5, 6, 7, 1 to 7. Right? And then another example, I could say it goes from 1 to 7 of I squared. Right? And what I do, I add up all the perfect squares. 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus 49. Right? Now, what am I doing? I'm summing all of the 2i's from I equals 1 all the way to I equals 7. So 2, 4, 6, 8, 10, 12, 14. All right. Now, there are some rules that we can apply when we're working with summation notation. And again, none of these are new, but we'll show you what they are. There it is, ready for me to go. Some algebra rules for finite sums. Okay. The sum rule. Number 1. The sum of k equals 1 to n, right? They use k for their index. I use I, because I stands for index. It goes from 1 to n of a sub k plus b sub k equals the sums separately. Now, does that make sense? At first glance, this may look like, what the heck does that mean? This is crazy. Let's take a close look at this. Let's say I'm going to sum from I equals 1 to, let's just say 5, right, to save a little space, of two things. I'm going to add I plus 2I. Right? Now, of course, we could just say that's 3I, but for the sake of spelling this out. So I plus 2I, that's going to be the number, the index, plus double the index. So it's going to be 1 plus 2 plus 2 plus 4 plus, let's see, 3 plus 6 plus 4 plus 8 plus 5 plus 10, right? So here's I and double I. I is 1, double it is 2. I is 2, double it is 4. I is 3, double it is 6. So that's all this is. Well, I can rearrange these. I can add things in whatever order I want. So this could be 1 plus 2 plus 3 plus 4 plus 5, right? I'm going to add all the first terms, plus 2 plus 4, 2 plus 4 plus 6 plus 8 plus 10, right? I can add things in whatever order I want. So what I will do is write this one simply as the sum of whatever it was. That was the sum of I equals 1 to 5, plus the sum I equals 1I to 5 of 2I. Right? So I can just do those two just like that. And I can break the sum of a mini-sum into its two separate sums. All right? Now, if you think about it, this difference rule is almost exactly the same thing. It's just subtraction instead of addition. Constant multiple rule. What am I really doing there? I'm factoring C out. Right? So if it's 7 times 1 plus 7 times 2 plus 7 times 3 plus 7 times 4 plus 7 times 5 plus 7 times 6 plus 7 times 7 plus 7, whatever, I could factor the 7 out, everything, and just put it out there and just deal with this sum as is. Right? Finally, my constant value rule means that if I'm just summing up some constant, right? C is any constant, 6, right? So I'm not. It has nothing to do with what the index is. I'm just adding 6 plus 6 plus 6 plus 6 plus 6 plus 6. Well, how many times am I doing it? That's n. So it's going to wind up being n times 6, right? So these all make sense. All right. Now there are some useful sums that come up here, and actually, maybe I've got room to write them down here. I'm on my next page of notes, but I can squeeze. So some common sums. The first one, of course, is the little one that Friedrich Gauss did. I'm going to say I equals 1 to n of just I. So I'm adding up the digits, 1, 2, 3, 4, 5, up to whatever. And as Carl did it, he said it is n, or it's 1 plus n, right? So that was kind of like the 50 plus, or the 100 plus 1, and he realized they all add up to that, times how many pairs there were, which is n over 2, right? Now, traditionally, that's written like this, n times n plus 1 over 2, and we can write that as a polynomial as n squared plus n over 2, right? It's most frequently written like this. This is kind of what makes sense as far as Carl's little trick that he pulled. This is how it's normally written. This is probably the most useful as far as a polynomial goes. All right. Another one that comes up a lot, I equals 1 to n of I squared. All right, well, how does that look? That's this one here, the bottom one on the left page. So I'm adding up all the perfect squares. That one looks very similar. In fact, it looks like this: n times n plus 1 times 2n plus 1. This time, all divided by 6. Right? Now, the reason that they're often written like this is because when we prove these sums, it's easier to write it like this. But it's more useful to write this one in its polynomial form: 2n cubed plus 3n squared plus n, all divided by 6. All right. And you might guess what the last one is going to be. And these, there's all sorts of these. You can go all the way up as high as you want. But the ones that we will use most frequently are the numbers themselves, just counting numbers, add them up, the perfect squares, and then the perfect cubes. And that becomes n times n plus 1 over 2, this whole thing squared. So it's funny that the sum of this is just the sum of the cubes is the sum of the individual numbers squared. Maybe it makes sense, but when you look a little more closely at it, it's like, what, does that really make sense? Not really. Now, one important thing to note here, and maybe I'll do this in yellow, is that notice when I'm adding up, I to the first, right, it winds up being n squared. When I add up I squared, it ends up being n cubed, and when I add up I cubed, it winds up being n squared squared, which is n to the fourth. Right, so the power always goes up by 1. Foreshadowing. Okay, so what's an example of kind of some cool stuff that comes up? One example I have is find the sum from I equals 1 to 5 again of, what if we did a negative 1 to the I power times I squared minus 1. All right, so it's nice to just practice writing these out. Okay, so I is going to go 1 through 5, so there's going to be 5 terms. When I equals 1, so let's write out 1, 2, 3, 4, 5. Right, when I equals 1, maybe we'll make a little table like this. So when I equals 1, this becomes a negative 1, right? Times 1 minus 1 is 0, so it becomes negative 1 times 0. When I equals 2, this flips to positive 1, and this becomes 4 minus 1, so that's 1 times 3. And then when I is 3, this becomes negative again. And this becomes, let's see, 3 squared is 9, 8, so that becomes negative 1 times 8. And then 4 becomes positive again, so it's 1 times 15. And at 5 it becomes negative again, so it's negative 1 times 25, 24. Right, so this thing equals negative 1 times 0 plus 1 times 3 minus 1 times 8 plus 1 times 15 minus 1 times 24. So this 1 is kind of annoying, isn't it? And we pay attention, all this 1 really does is, flips it back and forth. All the 1 does is cause it to alternate. So we could write this one as, well, the negative 1 times 0 goes away. So it's 3 minus 8 plus 15 minus 24. Right. Now this alternating thing will come up a lot next semester, but it's just kind of useful to see, if we have a series of numbers or sequence of numbers, and we're trying to come up with a summation notation to write like that, if it's alternating, this is pretty useful here. All right. Okay, so that's that. Now let's do a quick review of what we did the other day. And I believe we looked at something like this. We had some x and y axes, x and y. We had some parabola looking thing that kind of goes like this. That's a bad parabola. And then we went from, I think, 1 all the way to 2. And so this became a 4 up here. And we're trying to figure out the area of this, right? And we could, for instance, split this into 4 rectangles. And for my first one, I'm going to divide it into 4. So there's 1, 2, 3, 4 rectangles. And I'm going to use the right-hand corner. So I know that my area is going to be too big. Right, I already know this is going to be true, but I'm trying to estimate this area with rectangles. So that's how it's going to be. And this one goes all the way up here, and then comes down to there, right? Now this is easy enough to do because there's just 4 of them, right? 1, 2, 3, 4, and I could figure out what this area of the blue rectangles is. But let's try to write this in terms of sigma notation, right? Let's write it as a sum. So what's it going to be? It's going to be the sum of 4 rectangles, right? So I is going to be go from 1 to 4, and this is going to be the right-hand sum. And so I know it's going to be the sum of each of these, the bases, right? The base of each one of these is going to be, let's see, 2 divided by 4. 2 divided by 4 times the height, right? Well, what's the height of each one of these? It's how far did I go over, and I take that and I square it. So how far did I go over? Well, for the first one I went, let's see, let's draw these in and do the first one in orange. So to get to my first rectangle height, right, how far is this? That is 1 times 2 over 4. 1 times 2 divided by 4. Or I went over a half, right? How far do I have to go to get to my next one? Let's do that in green, right? The height of my next one is determined by 2 times 2 over 4. The height of my next one, we're going to run out of colors here, is going to be 3 times 2 over 4. And then my last one, back to yellow, will be, the height of my last rectangle will be 4 times 2 over 4, right? All right, so we go back over here, and using that, the height of my rectangle is I times 2 over 4. I times 2 over 4 squared. Okay? It's because this is how far I go over with each time, how far I move over for each rectangle, I times 2 over 4, and this is the base, right? And it's usual that this shows up twice, right? This is the base, and this is how many bases I've gone over. Now we know from our sigma rules that this is a constant, so this can come out. So this equals 2/4 is 1/2 times the sum of I times 2 over 4 squared. Right? Well, that equals, I can square these both here, so that's 1/2 times the sum of I squared times 2 over 4 squared, which is a half squared, which is 1/4. Right? Now that can come out too, right? That's a constant, that can come out, so that equals 1/2 times 1/8 times the sum of, now I'm just down to I squared. All right, and this is still going, I equals 1 to 4. But I know this sum. I know how to do this. That's one of my usual sums. Let's go back and take a look. I squared, okay? I squared n plus 1, 2n plus 1 over 6. Okay, let's write that down. So that equals 1/8 times this thing, which is going to be n times n plus 1 times 2n plus 1 over 6. And then, but I know that my n is 4, so I can plug all that stuff in. So it comes out to be, I think, 1/8 times, let's see, 4 times 5 is 20 times 9 is 180 over 6. And that simplifies down to 48 and divided by 4, 15/4. All right, so that equals 15/4, which is, let's see, how does that work out to be 3 3/4? So it equals 3.75. All right, but I know that's too big. I know that's going to be too big. So let's do the other one. Let's do the left sum and see how that works. Let's do the left-hand sum. All right. Now, if I do the left sum, let's do that in, let's see, the right-hand sum was in blue. So that's that one. And let's do the right-hand sum in purple. I guess I'm running out of colors. You know you're getting desperate when you have to pick purple as your color. So if we use the left-hand corner, this first one doesn't have any height, right? And the next one just goes up to here. And the next one just goes up to here. And the next one just goes up to here. So I'm way low here. When I use the left-hand sum, I know I'm going to be too low. Well, yeah, we picked rectangles, and we picked only 4 of them. So let's see what happens. This is the left-hand sum. Let's do a little work. Same deal. It's going to be the sum from I equals 1 to 4. And the base of the rectangles is still 2 divided by 4. Right? Because it's a total distance of 2 divided by 4 little rectangles. And the height of them this time, so even though it's my first rectangle, I have to go way back here to get my height. Right? I'm over on the lower left-hand corner here. Even though it's my first rectangle, my height comes from back here. So it's actually I minus 1 is how far I go over, times the width and all this squared. Right? Now pause this and think about that. Convince yourself that it has to be I minus 1 because I'm using the left-hand corner. I'm going way back here to get my x value that I use to square to get the height. Right? So my first one, 1 minus 1 is 0. 0 times 2 over 4 is 0. So I square 0. Yeah, that works out. The next one, I go all the way to 1. But then, or no, I equals 2. Right? So 2 minus 1 is 1 times a half. So even for my second rectangle, I'm only going over a half, so that works out. We can do a little algebra again. We can take this 2/4 out, 2/4, which is really just a half, times the sum of, let's see, if I distribute that thing, it becomes 2/4 I minus 2/4, and that thing gets squared. All right. And I can, let's see, what else can I do here? What do I do in this next step? I guess I can simplify that. That equals, these 2/4 are kind of awkward, so that's 1/2 times the sum of, let's write that as I over 2 minus 1 over 2 squared. Now if I FOIL that thing out, I'm going to get this, 1/2, and then I squared over 4 minus I over 2, right? Outside and inside combined to make I over 2, plus 1/2 squared is going to be 1 over 4. right? So FOIL this, you get this. If you don't believe it, pause and make sure that no magic tricks allowed here. Now this is just a bunch of sums. It's the sum of a mini-sum, so I can break that up into individual ones. So that's 1/2 times the sum of I squared over 4 minus 1/2 the sum of I over 2 plus 1/2 the sum of 1/4. All right. Now I can also factor that out, or I've got a bunch of constants in here that I can take out, right? This is really 1/4 I squared. The 1/4 is a constant. Let's get that out of there. So that becomes 1/8 the sum of I squared, which is nice because I know that one, minus 1/4 the sum of I plus 1/8 sum of just 1, right? And the sum of 1 is just, how many am I going to do? That's going to be 4, right? And these all go from I equals 1 to 4, I equals 1 to 4, and I equals 1 to 4 still. All right. Now, fortunately, I know this one. I know this is 1/8 times the sum of this thing is going to be n times n plus 1 times 2n plus 1 all over 6 minus 1/4. Right, this isn't one of my special sums. This is the one that Friedrich Gauss did. So this is n times n plus 1 over 2. And this is going to be plus 1/8. This just becomes n, right, which is just 4. So what does that equal? 15. Oh yeah, I've done this one before. 1/8 times all this stuff. I feel that looks very familiar. 1/8 times all this stuff. Yeah. So that just becomes 15/4. And then minus 4 times 5 is 20 over 2 is 10. So it's 10/4. And then plus 1/8 of 4, so that's 4/8 is 1/2 or 2/4. So this whole thing is going to equal 7/4. Now, at this point you might say, this sucks, right? And to some degree you're right. I did it one way and I knew it was going to be too big and I got 15 over 4. And I did it another way and I knew it was going to be too small and I got less than half of that, right? So this is a terrible way to approach this problem, right? Or is it? Let's take a quick review that if we go to this thing here, remember this from the other day, and this is not the function we want. We want just a parabola. And we're going to start with four rectangles. We knew that if we use the left sum, it's going to be way too small. And if we use the right sum, it's going to be way too big, right? But it seems as though, while both of these are pretty bad, if I really increase the number of rectangles I use all the way up to 40, all of a sudden the right sum's looking pretty good. But so is the left sum. And they don't look like either of those are too far off. So the question is, how many should I use? All right. And I think the answer to that question is, use an infinite number of rectangles. So that's what we'll do. Bye bye Mathematica. Let's move on to this. Next page. Oops, I went too many pages. Let's go full screen again. Let's make sure I didn't do too many pages. All right, there we go. So this is four rectangles. Now we're going to do an infinite number of sums, right? And this is now called, when we use an infinite number of rectangles, this is called a Riemann sum Bernhard Riemann, I think his name was. That's not very good handwriting. Important enough mathematician that I think his name, still bad, warrants good handwriting. A Riemann Sum. Holy cow. I'm going to have to edit this out. So, and we'll do the right sum first. Right, so we're going to do what's called the Riemann sum, an infinite number of rectangles. And we're going to use the right side. Now, this actually won't be too bad because what we're going to do is just take the limit as n goes to infinity of 2 over n, or the sum of 2 over n times I, right, how far did I go over, times the width of each rectangle squared. Okay. Now we can simplify this a little bit. So n for now is a constant, right? 5, 10, 100, 1,000. Right, we're going to take it to infinity later, but as for now, we're just going to treat n like a constant. So there's going to be a 2, and then a 2 squared, and then an n and an n squared, so that equals 8 over n cubed times the sum of what's left after the 8 over n cubed comes out? Just I squared, right? Which equals 8 over n cubed times the sum of I squared. Well, we know that one. It's n times n plus 1 times 2n plus 1 all over 6, right? And now we can do a little simplification here. This one writes, as I mentioned, this is the way we write it to prove it, but writing it as a polynomial is much more useful. Equals the limit as n goes to infinity of 8 over n cubed times 2n cubed plus 3n squared plus n all over 6, which equals, Algebra Fest continues, 16n cubed plus 24n squared plus 8n all over 6n cubed. Okay, now, what happens as n goes to infinity? When n gets really, really big, is this going to matter? So for a big N, that doesn't matter anymore. That doesn't matter anymore. So we're just left with the limit equals 16n cubed over 6n cubed, which equals 16 over 6, which equals 8/3. All right. So I claim that my area equals 8/3. All right, but the savvy listener says, oh, this is the right-hand sum. What about the left-hand sum? So, left side, is it going to be the same? Right? Well, let's take a look here. So again, what did we do? We said we did the right sum first, which we knew was too big, and we started with 4 rectangles, and we said, well, that's pretty bad, and so we can just keep increasing the number of rectangles we have, and that should approach the actual value. We're getting closer and closer and closer and closer, right? Well, if we do the left-hand sum, we know that's too small. But as we use more and more, we're gobbling up more of that area, so that should also approach the same thing. So whether we use the left side or the right side, it should come out to be the same. Let's see if it does. This is exciting. I hope you're excited. I'm excited. If you can tell by the tone of voice, this is exciting. All right. Now, this one gets a little trickier as to figuring out what we're adding up. We're going to, again, take the limit as n goes to infinity of the sum of a bunch of rectangles. The base of my rectangle is still 2 over n. Right? But how far do I go over? I don't go, for the first one, I don't go over I don't go over a rectangle, right? For the first one, I stay at 0. So it's going to be I minus 1 times the width of the rectangle, which is 2 over n squared, right? So why is it I minus 1? Because for my first rectangle, I don't go over a rectangle width. I stay right where I am for the first one. I stay at 0. So it's I minus 1. All right. This cleans up as 2 over n. Oop, I didn't mean to do that. It should be a lowercase n. Uppercase n actually means something a little different. So we'll leave it lowercase for now. Sum of 2 over n I minus 2 over n, that thing squared. And if we FOIL that thing out, this equals the limit as n goes to infinity of the sum. Actually, nope, I'm going to take out a constant right away. I'm going to take out this 2 over n right away, which I already did, I guess, of 4 over n squared I squared minus 2 times the product of these two, so it's 4 over n squared, plus 4 over n squared, which is just this one squared. Right. Now, same deal here. I've got the sum of kind of a mini sum in there, so I can break that up into its individual sums. Equals the limit as n goes to infinity of 2 over n times the sum of 4 over n squared I squared minus 2 over n sum of, let's see, that's 8 over n squared times I. Did I lose an I in here? I did lose an I. There should be an I here. Yep. I hope you caught that. 8 over n squared I plus 2 over n times the sum. Oh, I forgot my I there again now. I plus the sum of just 4 over n squared. All right. And again, I'm going to factor out all these constants. 4 over n squared is a constant. So this equals the limit as n goes to infinity of 2 over n, 4 over n squared. So that becomes 8 over n cubed times the sum of just I squared. Minus, let's see, that becomes 16 over n cubed times the sum of just I, plus, what was that, 8 over n cubed, times the sum of just 1 is all that's left there. All right. These are all my special sums, so I know these. So it's the limit of, let's see, 8 over n cubed times the sum of I squared is n times n plus 1 times 2n plus 1 over 6 minus 16 over n cubed times n plus 1 over 2, and then plus 8 over n cubed times the sum of that, which is just n. All right, but now here's what happens that's super cool. Guess what pen I'm going for, right? The red pen. This is going to be n squared over n cubed. As n goes to infinity, I better write this in here. Oh, you know I'm going to do it in red. As n goes to infinity, n squared over n cubed, that thing's gone. That goes to 0. N over n cubed, that thing's gone too. That goes to 0. So this limit then really just becomes defined by only this term, which looks awfully familiar. 8 over n cubed, nn plus 1, 2n plus 1 over 6. 8 over n cubed, nn plus 1, 2n plus 1 over 6. It's the same thing, right? And that equals 16n cubed over 6n cubed, which equals 16 over 6, which equals 8/3. How cool is that? All right? We get the same answer either way. Area equals 8/3. Either way we do it, we get the same answer. That is the exact area under a parabola. So, 41 minutes into it. I hope you found that somewhat interesting. I certainly find it very interesting. So, if you have any questions about this, we'll get a chance to talk about it. Take care, folks. Thanks for listening.